Humans have always looked into the night sky and wondered, who are we? Where are we? Are we alone? 100 years ago, a common understanding was that our galaxy, the Milky Way, was all there was. But now we can see more than 100 billion galaxies, and astronomy is on the verge of seeing light from the origin of the universe. How has this become possible? This building is Steward Observatory at the University of Arizona in Tucson. It began as one building with one telescope. Now, Steward Observatory has become much more than this one building. It is an institution of many telescopes and laboratories and people. It is the only lab in the world where massive telescope mirrors are made. It is a pioneer of infrared astronomy, which reveals what was once invisible to the eye. And it developed some of the most complex astronomy instruments for use in space. Why Steward Observatory came to be and what it gave birth to is the story of visionary people, the events of the modern age, and the human need to understand our place in the universe. This is the story of Steward Observatory. The roots of modern astronomy in Arizona stretch back 150 years to a chance encounter between two New Englanders, one of whom was consumed by the desire to find life in space. Percival Lowell was born to a wealthy Massachusetts family. A graduate of Harvard, he thought of himself as an astronomer.
He had a lot of money, and he was interested in the planet Mars. And in those days, if you had the money to build your own observatory, you became an expert in that field, no matter what your educational background was.
The other New Englander was Andrew Ellicott Douglas, a 28-year-old with a bachelor's degree in physics.
So he hired the young Douglas to come out to the Arizona Territory to find a location for his telescope and to build the observatory.
Flagstaff is where the first major observatory in what was then the Arizona Territory was built. Douglas oversaw the construction of and helped build Lowell's Observatory.
You know, the world was smaller and the science enterprise was smaller and people weren't as specialized, and it was a kind of wild frontier, so, you know, you had to make it up as you went along.
Arizona, in its early days, picked up rugged individualists. They decided what they wanted to do and they got out and they did it.
Lowell would come out from time to time and make observations, but it was basically from 1894 to 1900, A.E. Douglas ran the Lowell Observatory.
At the turn of the 20th century, conventional wisdom held that there was a civilization on Mars.
There were Martians, because Mr. Lowell said so, and he had the biggest telescope that was looking at Mars.
Douglas would draw by hand what he observed on Mars. Lowell used these sketches to create his own imaginative drawings of Mars.
And then he came up with an entire story of a dying civilization on a planet in a desert-like state, and canals are brought down from the ice caps of Mars to bring water to the Martian civilization. And of course, some of the articles published by Lowell would inspire H.G. Wells to write The War of the Worlds.
One winter night, Douglas observed unusual activity on Mars. This was the sighting Lowell had long hoped for.
Douglas was at the telescope in Flagstaff observing Mars. Douglas saw something that looked like a wisp, like little wisps.
For Percival Lowell, those wisps were proof of life on Mars. But to A.E. Douglas, they proved nothing. Douglas publicly disagreed with Lowell and lost his job.
Douglas was basically fired for being a good scientist.
Jobs in professional astronomy were not abundant in those days. At the age of 40, A.E. Douglas took a job at the University of Arizona and began a new career teaching geography and physics. From the moment Douglas arrived in Tucson, He wanted to build an observatory that rivaled the Lowell Observatory in Flagstaff.
There were only 3 larger telescopes in the United States, so he was trying to do something fairly substantial.
In those days, you realized that the federal government or any sort of government entity didn't start funding basic science until after World War II.
Because neither the university nor the state were interested in funding the proposed observatory, Douglas turned to private donors.
In October of 1916, they were able to announce to the press that Mrs. Lavinia Stewart had given a $60,000 grant to the University of Arizona. It was the largest private grant that the university had received up until that point.
The observatory was built in a distant corner of the empty campus. Construction, interrupted by World War I, took nearly 4 years. Once the observatory was complete, the telescope arrived on campus in pieces, hauled from the train yard on horse-drawn wagons.
Douglas is the architect who designed the building. He's the one that decided the size and scope of the telescope, and he would also decide on the scientific program to begin with at the observatory.
Douglas and Southern Arizona now had their observatory. The first public evening was held in September of 1922.
He opened the observatory to the general public because he wanted them to share in the wonders that were to be discovered by his telescope.
Science was to change dramatically in the years following the dedication of Steward Observatory. Those changes were driven by the new global realities following World War II and the ensuing Cold War. Astronomy changed as well. Steward Observatory and Southern Arizona would play a prominent role in the many developments to come.
The National Science Foundation got started around 1950, a recognition that there was tremendous brain power that could do a lot of creative things as a result of World War II. America ought to create a strong science foundation to essentially become the research arm of the country.
The federal government decided to create a national observatory. Astronomer Aidan Meinel was appointed to head it and find a place to locate it.
Having a facility open to all astronomers, all universities, was really important at that time. So they needed a place to locate it that had to fit some restrictive requirements. It had to be, of course, a good astronomical site, an excellent astronomical site, but it couldn't be so isolated that it was impossible or very expensive to get to.
You're always balancing the cost of having a telescope in a really excellent place, extremely far away, with getting one closer where you can have it working as well as possible. And that's always been the great advantage of Tucson.
Meinel selected Kitt Peak, 50 miles west of Tucson, as the location for the new National Observatory. Meinel himself designed Kitt Peak's first telescope and had the site in operation by 1960. Kitt Peak soon became a world-class observatory and the cornerstone of a telescope boom in the Sonoran Desert.
So during the 1950s, there were very generous appropriations, and those increased during the 60s and 70s. And universities were able to ride that tide and really build strong science establishments.
Aidan Meinel was appointed director of Steward Observatory in 1963. Under his leadership, Steward Observatory began a decade of remarkable growth. Meinel relocated Douglas's 36-inch telescope to a new Steward Observatory building on Kitt Peak.
Aidan was one of the most creative people I've ever met. And during the 3 or so years that he was the director of Steward Observatory, he basically put together the proposal through NSF and the state legislature of our 2.3 meter, 90-inch telescope on Kitt Peak.
Meinel's next significant contribution was to help develop a telescope, utilizing several mirrors in unison.
Using light collected by several different mirrors was really a breakthrough from the concept you just got to keep on building bigger and bigger mirrors.
All big telescopes have to take this step of using multiple pieces of glass to make the mirror, and the MMT was the first one to take that step.
That became then the way that all modern telescopes from the 1970s have been built and will continue to be built.
As those modern telescopes populated the peaks surrounding Tucson, a fundamental shift occurred in how they were used.
In terms of astronomy in Arizona, it was virtually all visible light astronomy using photographic plates and essentially done just from Kitt Peak.
The visible spectrum is how our eyes see the night sky. Astronomers now have a way to see light from the infrared spectrum, what is otherwise invisible to our eyes.
There's a lot of things in the night sky that are completely invisible to our eyes. These are things that are objects that only appear in the infrared. And many things are much brighter in the infrared than they are in the visible.
You assume that as soon as you develop the technical means for a new kind of astronomy, it happens. But infrared astronomy had those technical means in the 1920s. And finally in the 1960s, people got really interested in it, and one of the key people was Gerard Kuiper.
Gerard Kuiper established the Lunar and Planetary Laboratory at Arizona, where infrared astronomy was pioneered. The leading figure in infrared astronomy was Frank Lowe. Using instruments of his own design, Lowe began to observe planets in our solar system. New discoveries came very quickly.
Frank had discovered that Jupiter actually has so much energy stored from its collapse that it is currently radiating about twice as much energy as it absorbs from the sun. There's hardly an area of astronomy that hasn't really been impacted by the capability in the infrared.
The ability to look at molecules, which is one of the key things that infrared astronomy can do, is going to be huge for studying planets around other stars. It's just a whole nother look through the universe.
In the early 1970s, the Steward Observatory began to dramatically increase the power of ground-based telescopes. Peter Strittmatter, new director of Steward Observatory, helped guide and shape that work.
When Peter joined Stewart Observatory, although it was doing well, it was by no means one of the best places in the world to do astronomical science. It just wasn't. When Peter left as director some 37 years later, you couldn't imagine that anyone would have anything other than a world-class opinion of Stewart.
He took us from a modest-sized place to a frontline place. And that was all due to his vision and hard work.
Peter just kept building, expanding, coming up with new ideas, being very creative. And a cautious bureaucrat would have stopped him many times, but the university, to its credit, didn't do that.
One of Peter Strittmatter's most significant accomplishments was supporting the creative work of a singular scientist and the experiments he conducted at home.
I certainly melted glass at home, right, in a little small furnace, just to get a sense of what happens when you melt glass. And then we moved pretty quickly here on campus to make bigger furnaces that would melt glass to form the honeycomb structure.
Building on these experiments, Roger Angell proposed using a rotating furnace to better shape the molten glass, and thus the Steward Observatory Mirror Lab was born.
Newton worked it all out, how it would work, right? How if you spin a liquid, you'll get the right curve on it.
It's non-trivial to build an 8-meter sized furnace that spins, multiple times a minute, can heat glass to its melting point and keep spinning the entire time.
By the late 1990s, the Steward Observatory Mirror Lab successfully cast the largest mirror ever made. In fact, they made 2 of them. The 2 mirrors are the eyes of the world's largest optical telescope, the Large Binocular Telescope on Mount Graham near Tucson.
There's no other lab like it in the world, not even in private industry. They were not willing to take these sort of chances, so it's rare that a university lab can innovate, on a scale, on a really industrial scale.
The lab has to live by its wits, right? Nobody in Washington sends a check each year to keep everybody paid, right? People are only paid if we have work to do and mirrors to make.
Even though telescope mirrors got much bigger, these giant mirrors have to look through the dense atmosphere of Earth, which distorts light before it reaches the telescope.
We were building these giant mirrors, but they weren't making images any better than small telescopes because the atmosphere above the telescope limits the sharpness of the images.
The Steward Observatory Mirror Lab explored techniques to eliminate this distortion. Adaptive optics was the solution.
In parallel with Roger working on these mirror technologies, Nick Wolf was doing a lot of the theory of how you would cheat the atmosphere, which is essentially what adaptive optics is doing.
Imagine a mirror that's sort of rubber-like, and you're changing the shape of that mirror 1,000 times a second. And you have to, of course, move it to not just any shape, you have to move it to exactly the opposite aberration that the atmosphere is putting into the beam. In a nutshell, with clicking a mouse, you could make an image that was as good as if the telescope was in outer space.
What's more important about it is it's changed people's concept of how to build really big telescopes. And now the whole rationale for 20-meter, 30-meter telescopes is based on using adaptive optics to sharpen up the images.
As ground-based telescopes dramatically increased in size and sensitivity, a radical development for astronomy was to place telescopes in space. Stewart Observatory has helped this development from the beginning.
The initial forays into space astronomy were mostly ultraviolet or X-ray missions. Then the Hubble Space Telescope came along, and that was the first time that your rank-and-file astronomer got interested in space astronomy because they were used to observing at those wavelengths and they could think through what projects would be.
The Hubble has one infrared camera. The more recent Spitzer Space Telescope has 3 infrared instruments. Steward Observatory played a key role in developing all of them.
You quickly realize that you need a big telescope because you'd like it to have Hubble-like resolution and clarity, but more like a Spitzer range in wavelengths. And so that leads you to wanting a big telescope, a cold telescope.
The biggest, coldest, and most complex space telescope ever imagined is the James Webb Space Telescope. 2 of its 4 instruments are linked to Steward Observatory.
It is a huge telescope, and therein lies some of the complication. Because it's so big, we can't launch it as a single mirror. That's why it's comprised of 18 segments, and it folds up like a piece of origami in the nose cone of the rocket.
It will take nearly 30 days for the James Webb to unfold and assemble itself in space while traveling to its observation post 1 million miles from Earth. The core mission of the JWST is to observe what is called first light, the light generated in the immediate aftermath of the Big Bang.
It'll be interesting to see if the first things that we can identify as galaxies, do they show evidence of there having been a previous generation of stars, or do they have the first generation of stars themselves? There are a lot of questions like that we don't know the answer to.
Back on Earth, Stewart Observatory is helping to build the giant Magellan Telescope, located in Chile's Atacama Desert, over 8,000 feet above sea level. The giant Magellan is part of the next generation of very large telescopes. All the mirrors for the giant Magellan Telescope are being cast and polished at the University of Arizona.
When we get the GMT 20, 30-meter telescopes and adaptive optics, then the ground-based telescopes will be able to have much finer resolution even than JWST.
By building the giant Magellan, we're laying the foundations for the astronomy in Arizona for the next several decades.
Probably the killer app for the GMT is going to be diagnosing the atmospheres of Earth and super-Earth-like planets. Not a huge number, but maybe a dozen or so, and trying to see alteration of those atmospheres by microbes, which would be the first detection of life anywhere else, so that will be a millennial-type discovery if it happens at the GMT.
Can we actually find the biosignatures of life and living worlds out there? And that's the exciting sort of scientific questions that are driving the next generation of telescopes, like the Giant Magellan Telescope.
In scale and complexity, the GMT is light years beyond the observatories made by Percival Lowell or A.E. Douglas. It is also massively expensive, a $1 billion project founded upon an international collaboration of universities and nations. And as government funding of astronomy has declined, support from private individuals matters as much now as it did in 1916, when Lavinia Stewart made a donation that led to the first major observatory in Tucson. 100 years later, a donation of $20 million from Richard F. Karras has helped assure the next generation of astronomy and research in southern Arizona. The Richard F. Karras Mirror Lab is where all 7 mirrors comprising the GMT are being made. A.E. Douglas began the Steward Observatory. One might well wonder what he would make of it today.
He said this in his dedication. Stewart Observatory shouldn't be treated as a monument. He said it's a living, working observatory.
Douglas also told his audience, research is knowledge acquired before it is needed. The discoveries of the past 100 years have proven him right.
You know, how are we learning about our place in the universe? God forbid we should ever have to find another habitable planet to move to, but if we know nothing about the universe and we need to do something radical, we'll have no idea if we haven't studied what the universe contains.
We know we have our little short time frame as humans, but what's the role of humanity as a whole? And especially when it comes to trying to find life elsewhere, which is what some of these large telescopes will be trying to do, that's really setting us in a very large scene where we wonder, are we the only ones with existential angst with all the problems we're dealing with? It's Buckminster Fuller quote, either way the implications are staggering, we're alone or we're not. And astronomy is really poised to answer that question too.